Maximal Atlas on logical manifold M. Maximal Atlas on logical manifold M is an atlas if it is maximum. In other words, it is not contained in any other atlas. Okay. If it is not contained in any other atlas.
तो और एटलस है तो वो इसके अंदर तो और एटलस है
इसके अंदर कंटेंट है. If it is not contained in any other atlas. In other words, आप कोई भी चार्ट सोचे ये मैक्सिमल एटलस उसे कंटेन करती है. ठीक है. So think of any chart. Maximal Atlas contains it.
Collection of charts.
It's a collection of charts, but it's a kind of a collection of charts that, okay, that what? It's a collection of charts that kind of a collection of charts that all other collection of charts are subsets of. So I would say that is, इसको मैं यूँ भी लिख सकता हूँ. If Maximal Atlas, let me give it a symbol, calligraphic A. So if calligraphic B is another atlas containing A, ठीक है. तो फॉर एग्जाम्पल एक और एटलस है जो कि इस पोटेंशियल मैक्सिमल एटलस को कंटेन कर रही है. देन कैलिग्राफिक बी दिस इज व्हाट. ठीक है जी. सो नाउ आई होप definition is pretty simple. I need smooth, so if I want to define smooth manifold, I must have a topological manifold with this maximal atlas. Now the trouble with this definition is, the serious definition is, how to find a maximal atlas. In other words, you know, if I have to cover a circle, I can cover it with, you know, okay, two half circles, maybe, 4 half circles, or maybe 4 pieces of quarter of circles. Are you getting the point? So I can cover it with many what you call kind of atlases. But how to find a maximal atlas? What the previous result allows us basically that if you have any atlas, for a given atlas, you can always find a unique maximal atlas actually. Okay? For any given atlas, with any number of elements in it, you can always find a unique maximal atlas. In other words, if on a manifold you have a simple atlas, you can always extend it to the maximal atlas. That's it. So in other words, if on a topological manifold you have a simple atlas, it's enough, to have it, because if you have this, then you can extend it so much and so forth that you're going to have the maximal atlas. Is it making sense? Okay, this is an important theoretical point to understand, that when I'm defining or when I'll do the examples of smooth manifold, I'm not going to create maximal atlas. I'm going to start with an atlas, and that atlas is enough actually.
Simple atlas means any atlas.
Any atlas. So let me state this in the form of a lemma. Okay. State this in the form of a lemma.
तो सर हर मैनिफोल्ड के ऊपर एटलीस्ट एक तो होगा ही होगा।
So it's anomalous thing. So if you have a topological space, topological manifold, okay, which every point has a neighborhood that is locally Euclidean, okay, and along with that you have an atlas on it, then it's a smooth manifold. Okay. But if you are calling it manifold, you are assuming already atlas.
Yes.
Okay. So don't call it manifold. So here's a proposition. So any atlas, U alpha, phi alpha, U alpha, okay, on a topological manifold M, okay, is contained in a unique maximal atlas. Unique maximal atlas. ठीक है? Why this would be the case? So I'm not proving it, I'm just giving you just a hint, because the previous lemma, is basically, from previous lemma you can deduce this. Think about it. Imagine you have a C infinity atlas. Okay? It's not necessarily maximum. But you found two other charts which are compatible with C infinity atlas. Then they are also C infinity compatible. Okay? Now if you add these new charts into your previous, what do you call, atlas, you're going to get an extended atlas. Are you getting the point? So I can keep on adding, what do you call, charts, okay, C infinity compatible charts into my existing atlases, okay, and I can ultimately reach to, what do you call, a one bigger atlas, okay, and we can also easily prove uniqueness. You can read the proof from book. Okay. So what would be the ultimate, what do you call, conclusion of all this theory? So if I summarize this, this previous 3 lectures into a one line, okay, the summary is this. If I want to prove an M, a manifold, so M को अगर मैं manifold show करना चाहता हूँ, याद रखें, if I am not using any other suffix or prefix with it, I mean a C infinity manifold or a smooth manifold. So if I have to say a topological manifold, I will say it. Okay? I will not just say, So if I want to show M is a manifold, I need 2 things. Number 1, phi is M is a topological manifold. Okay? And phi, you have some atlas, and by atlas I mean C infinity atlas on it. If you have, then M is a smooth manifold. That's it. So you always want to have these 2 things. First you want to verify the given thing is a topological manifold, and the other thing that you want to verify is that you must have an atlas on it. That's it. And that would be a smooth manifold. Okay, so this is what the key thing is. Okay, definition, I'm saying again, definition requires a maximal atlas. Okay, but I can make this condition weaker using this lemma that since any atlas is ultimately going to go, or you can extend it to the maximal atlas, so any atlas would work. Okay.
सर यहाँ पर आपने C infinity नहीं यूज किया तो इस definition में थोड़ा सा
Okay, it's everything is C infinity.
अच्छा ठीक है
When I'm writing Atlas, C infinity Atlas.
सही
Okay, in other words, all transition maps are C infinity.
सही
Okay, this is what is the key thing. Now I would like to do the core of our things is basically I would like to do some examples of smooth manifolds. So we did examples of topological manifold, but I want to do enough number of examples of smooth. Okay? And this is an important thing that we must basically realize theoretically, that what kind of things we are talking about. Okay, I can memorize this definition. I can say, okay, M is a smooth manifold if it is a topological manifold. In other words, it locally look like Euclidean space, and you have some atlas on it. But what is going on at the backhand, it is very important to understand it at least once in life, okay? Because if that part of understanding is missing, then when you want to do, for example, things on manifold, then those things are going to haunt you if you don't have the basic theoretical things. Okay? In this course, we'll not be interested in general smooth manifold. We'll define it. Okay? We'll be interested in a very particular kind of, basically two particular kind of manifolds. One is curves, okay, that we have already done. Another is surfaces, basically. Okay, that is our next task. We want to do things on surfaces. Alright, so let's do some examples. Example number 1. Let's take Rn. Any n-dimensional vector space. Is it a manifold? Another smooth manifold. Number 1, I need to say that is it a topological manifold? We have seen it already.
Yes, sir.
That it's a topological manifold. So the only thing that you need is atlas actually. So what would be the atlas on it? What would be the atlas on it? It's going to be a singleton basically chart, in which the open set is Rn itself, okay, and the chart map is the identity map. That's it. Okay. So Rn is a smooth manifold. Any n-dimensional space is a smooth manifold. Okay. And hence anything that is isomorphic to n is also a smooth manifold. Think about it. So first example. Let's do the second example. Let M be a manifold in the sense that we have. Let U be an open subset of M. Okay? Then claim is that U is also a manifold. It's basically a submanifold of a manifold. It's a manifold. You should call it a submanifold as well. Okay? Question. How can I show that this open set is a submanifold? Okay? This open set is a submanifold. So in order to be manifold, it must have two things. Number one, it must be a manifold. You must have an atlas. Okay?
Same.
By the way, why U is a topological manifold? We have discussed it previously. Because you can have a similar, what do you call, chart, U and identity of U. Okay, so that could be what you call a chart of it. So it's a topological manifold. So if I want to have an atlas from it, what should I do? I know that M is a manifold. So I can borrow the atlas from here. Think about it. So here's the thing. So if A, which is phi alpha, U alpha is atlas on M. Now give me the atlas on U. So in other words, if I take a chart from manifold, can I create a chart? Let's think about the intersection actually. Okay? Intersection. So I need a, first of all, chart map. So the chart map is going to be what?
Restricted.
So it's going to be a phi alpha, the same map phi alpha, but restricted where? U intersection U alpha. Okay? Obviously it's a map from U intersection U alpha into Rn, R may be the phi alpha of U intersection U alpha. Let's call it Rn or whatever. Take it. And what would be the open sets in this chart? So it's going to be U intersection U alpha. So hence the atlas for the open set U is this restricted phi alpha. So I can give it some name. Maybe phi alpha U, something like that. Okay. Phi alpha U. And the charts would be U intersection. So that's an atlas on U. Okay. So now I can claim that if you have a manifold, then any open subset of that given manifold is a, is also a smooth manifold. Okay. That's the second example. Let's move on. Let's take S1. S1 is the collection of the points from R2. I can treat it as x squared plus y squared is what we call circle. Okay? What I need to show? I need to show that it's a smooth manifold. Okay? So we previously discussed that it is a topological manifold. The only thing that we'll be interested in is that what is the atlas on it. Okay? So the atlas on it, we also basically constructed it yesterday. I mean, if you remember. Okay? We constructed it yesterday. We constructed, so I'm not getting into it again, just giving you a quick go with it. Let me just recall you that what was U1. So U1 is collection of cos t, sin t, such that t is between
minus pi
and minus pi to pi. And U2 is cos t sin t. Okay? And t is between 0 to 2 pi. Are you getting the point? Okay? So it's like I have a circle. So So this U1 is covering everything, okay, except a point of the circle, and U2 is covering everything except any other point of it. And if I combine them both, obviously they cover, your S1. We also defined phi 1s and phi 2. I'm not getting into it. What definition we proved that their smoothness and everything basically. So for circle, I have this atlas. Phi 1, U1, and phi 2. So we're going to say that this circle is a smooth manifold. Okay? By the way, in the book, I'm going to send you all these notes today. In the book, you will find another atlas for the circle actually, which consists of the 4 charts. Okay? And all are C infinity. And so here's the thing. So I have 2 charts. They're going to take me to a maximal atlas. And another example that you're going to do, okay, consists of, for example, the 4 charts that is also going to take me. So what are those 4 charts is basically this. That, okay, you take these 2 pieces, that's U1, U2, okay, and these 2 pieces take U3 and U4 actually. So these U1, U2, U3 and U4 are going to cover this what you call it. Okay, and with some flaws defined it. You can go through it for yourself.
Sir,
So you're going to have another atlas, huh?
इस केस में अगर हम maximal का सोचें तो वो कौन सा?
That's it. So the maximal atlas, I don't know what would be the maximal atlas in this case, but I know that since I have these 2 atlases, so they must take us to one maximal atlas. You can't have, for every maximal atlas you have a different, for every atlas you have a different maximal atlas every. Maximal atlas is going to be only variable one. So in other words, in order to prove, so if I want to prove this object a manifold, I just need to define few things. How I want to cover it, okay? And what would be the chart map? That's it. And I know that I can cover it in many ways actually. I can put it in a sphere, I can put it in a box, I can, wrap a, page around it. I can do many crazy things with it. All these are going to be basically what do you call, if they are smooth, atlases. Okay, so you can have multiple atlases for a given, what do you call, manifold. Okay, are we happy with this? So, let me do another example. And then, in other words, let's extend this S1 to Sn actually. Okay, I can do S2 or S3. By the way, this S1 is a one-dimensional manifold actually. Okay, one-dimensional manifold. Because if you remember, phi's were the maps which were taking this as an input and giving you the number t as an output actually. So they are one-dimensional manifold. Okay. So let's talk about a bit of generalization of this example. So instead of taking S1, let's take Sn. So let's take a hypersphere. Okay? And whenever you hear word hyper, it means it's something beyond 3 dimension. Okay, 4 dimension and so on and so forth. Okay, so hyper allows हमेशा higher dimension के लिए 3 dimensions का higher इस्तेमाल. By the way, there was one thing that I missed. I must have talked about it. Okay, so let's discuss and then take this. Let's spend the rest of the time only doing one examples, making sure that we see different kind of examples. So let's take sphere. Let's take Sn. Okay? And what is, so it's a hypersphere. So hypersphere is going to be the collection of the points in what space? In what space?
Rn.
So see, S1 is a one-dimensional manifold. So it contains points in
R.
R2. So it's going to be n plus 1.
N.
So it's a collection of the points from Rn plus 1 such that the magnitude of the norm of the x is 1. Okay, so this is what you call is what would be the atlas on it? Okay, the atlas. So that's on sphere. You can find many different varieties of atlases, but I want to what do you call take the very basic one. Okay, how do we make basically the maps of map of a world actually? That's what I'm not telling you. So world is a two-dimensional object. Okay, it's just a sphere. So two-dimensional object sitting in 3 dimensions. That's our assumption. Okay, maybe it's sitting in higher dimension. Let's assume it's 3 dimensional. Okay. So how we can project something that is sitting in 3 dimensions, which is a 2-dimensional object, onto some flat space? Because if you want to make the, what do you call, the map of the world, you want to project that sphere onto, what do you call, flat space. Actually, it is impossible to do it. It is impossible to do it. You can't put, no matter how hard you try, you can't make or turn a sphere into a flat space. Okay? But what we can do something interesting. Think about it. So imagine, go to the sphere and just take out any one point or make a hole in it. Make a small hole in it. So in other words, okay, go to the North Pole and just take out that point. So you're going to have a what? A sphere with, so punctured sphere with one hole at it. Now it's no more a sphere, basically if you puncture it. Okay? Now think about it. So that's a topological space. Okay? So what can I do is that I can make that hole that looks smaller, I can make it bigger. Okay? In other words, I can invert, it is possible to invert the sphere. Even it is possible to flat it actually. Think about it. So I have this page. So I have this page with me. If I wish, I can try to make it a sphere. It's not going to be a complete sphere. Okay. It's not going to be a complete sphere, but I can try it at least. Okay. So you can already imagine it that if I have something flat, I can try to make it a flat. But there would be some points missing actually. Okay. I can't totally turn it into a flat. Okay. If I, for example, if I push it and join it forcefully, then this would violate actually for many, many points. Okay, the distance from the origin is not going to be always 1. Okay, unless you leave some space. Are you getting the point? Okay. So this is what essentially what we want to do, and this is called the stereographic projection. That okay, you take the sphere, you poke a hole in it, okay, and then you try to define a map, okay, that takes a point from sphere and throw it on a plane actually, say XY plane. Okay? So now you can get your sphere turned into, what do you call it, plane. And this projection is called the stereographic projection. So I hope almost all of you have understood this visualization, what I am trying to say. So I am saying that, imagine I have this sphere. I can show it in a circle. Think about it. So I'm saying that I have a circle here, and I'm making hole, what do you call a hole in it. So I'm just removing one point. Then this circle is no more a circle, it's a line now. So think about it. Topologically, I can take it and stretch it and bend it and turn it into a line. Yeah, it's not a big deal. if I say, okay, what are the stereographic projection is doing? The stereographic projection is doing this. It's saying this, that take this point that you have removed from it, okay, and take this line. Okay, we say that take a point on sphere. I want to